Hi, my name is Ken Holstein, and in this talk, I'll discuss work with Bruce McLaren and Vincent Aleven on methods to study the effects of classroom context on student learning and behavior within educational software. I'll start with some background on a class of learning technologies called intelligent tutoring systems, for those unfamiliar, and then introduce a new visualization method and an associated tool prototype for triangulating within software and out of software classroom data. Then I'll present a case study demonstrating how we've used this method as part of an analysis workflow in our own work. And finally, I'll discuss some challenges and next steps for future research. So very quickly, at a high level, the behavior of intelligent tutoring systems can be understood as a feedback loop in which students take actions in a software interface, and the intelligent tutor updates its model of the student's current state, which could include any of various real-time analytics, detecting whether the student seems bored or is making lots of careless errors, diagnosing their mastery of certain skills, or whether they have particular misconceptions, and so on. And finally, the intelligent tutor uses this model to decide what to do next, which could come in the form of what sort of feedback to give, in the form of step-level text-based hints, for example, or what math problem to give to a particular student next, given their current state. So several meta-reviews have indicated that intelligent tutoring systems can enhance student learning in classroom settings, compared with traditional classroom instruction and other forms of educational technologies. And another key advantage of intelligent tutoring systems is that when used in classrooms, they may free the teacher to provide more one-on-one support to students who need it most. From a learning sciences research perspective, the analytics generated from students' interactions within the software can and often have facilitated fine-grained process analyses of student learning and behavior. So the effectiveness of intelligent tutoring systems is commonly evaluated through in vivo studies. They examine the effects of these tutors in the context of classroom contextual variables that are likely to be present in real environments of use. So these might include collaboration between students, help from a human teacher or a peer, or various external distractions. However, in these effectiveness studies, the effects of classroom contextual variables themselves are not typically measured. Instead, these are usually treated as background noise to be averaged out. Yet there's good reason to believe that certain aspects of classroom context may need to be considered more explicitly by ITS designers. For example, a large-scale 2-year evaluation of the Carnegie Learning Algebra 1 system suggested that variability in the out-of-software support that teachers provided to students may have been at least partly responsible for inconsistent results across evaluation years. And recent work from Raka and others suggests that even students' spatial arrangement in the classroom, in the context of a classroom lecture, could influence their engagement. So to help us get a better sense of how classroom contextual variables might influence student learning and behavior in ITS classrooms, we developed a prototype of a replay system called SPACLE that enables researchers to examine both within and out of software behaviors in the classroom simultaneously. SPACLE uses the log data that's already generated by intelligent tutors, but can also display out-of-software observations, such as help from a teacher or student collaboration, which could be recorded either manually or automatically via physical sensors. Exploration of individual class sessions with SPACLE can then inform the formation of hypotheses, which can in turn be investigated more rigorously through causal and predictive modeling using data from multiple classrooms. So this is a simple example of a SPACLE replay running on data collected from a classroom study. The teacher is shown as this dot moving around the classroom from student to student, and the dot sometimes changes color to indicate what actions the teacher is taking. At the same time, you can see student variables displayed on individual students' screens, and here shown on a spectrum from black to green. And a few high-level takeaways: the teacher often appears to provide seemingly unsolicited help to students during lab sessions. And it also seems like whether or not students go off task may be related to the teacher's location. So in this example, only one variable is displayed for each student, but the tool can visualize any variables that can be computed from analytics generated from the tutor, or the raw log data. So although this won't be the focus of this talk, we can also use spatial replays to investigate teachers' awareness of their own behavior in the classroom and identify potential blind spots. For example, when we asked some teachers who participated in a recent classroom study to walk through what they did during a class session, we found that their recollections often seemed to diverge from reality. So this teacher recalled being constantly active throughout the classroom when in reality, a very large proportion of the class time was spent inactive. And many students did seem to go off task exactly during the times when the teacher had their back turned to the class for long periods. Some recent work in educational data mining has begun introducing tools that can supplement analyses based on log data from intelligent tutoring systems with more context-rich data streams. So, for example, Ran Lu recently introduced a tool that allows researchers to click on particular regions of learning curves in the data shop system and view webcam recordings of individual students working in the software during that period, collected from their laptops, for example. By comparison, by visualizing a relatively small set of features within an interactive replay, SPACLE may enable faster detection of qualitative patterns across multiple students in a classroom. So to quickly give you a sense of the process of building a replay with SPACLE, SPACLE accepts log data from educational technologies in DataShop export format, as well as quantitative classroom observation data in a standardized format. So SPACLE extracts student names from the data sets and allows researchers to upload a seating chart, often provided by the teacher in our case so far, and then drag and drop student visualizations into place, which are later dynamic. Then researchers can select custom real-time analytics to display in a particular replay, for example, as custom written scripts, and assign colors and numerical thresholds for indicators that will be displayed. And these settings can then be interactively adjusted during a replay to facilitate exploratory data analysis. So to illustrate where SPACLE can be used in data analysis workflow, I'll describe how we've used SPACLE replays in one of our own recent investigations. Throughout, we've found it very useful to move from contextually richer methods such as classroom observations and replay analyses on smaller samples to more generalizable methods such as causal modeling on larger samples, and not necessarily in a linear fashion, as I'll show. So we started with qualitative observations in classrooms using intelligent tutors and generated questions around the observation that human teachers were often providing students with out-of-software help, which was not necessarily anticipated by the designers of these systems. After these class sessions, we checked for learning gains by comparing students' scores on a pre and post test. And then we moved back up on the contextual richness scale to spatial replays, using a small subset of our data, just a couple of classes, to investigate how out-of-software phenomena we'd observed in classrooms might have influenced student behavior within the software. To evaluate the robustness of relationships we'd observed in these replays, and also to discover mechanisms that might explain some of these relationships, we conducted mediation analyses on a larger data set using both tutor log data and classroom observations. And finally, we moved back up to replay analyses to help us interpret results from our quantitative analyses in cases where they weren't so conclusive. Multiple hypotheses were compatible with the data. So in these analyses, our initial informal observation in live classrooms led us to wonder whether and how student learning is influenced by teacher behavior during these class sessions. And there's been surprisingly limited consideration of the role human teachers might play in classrooms using intelligent tutoring systems in particular. So to illustrate, the intelligent tutoring system literature has generally defined help-seeking as synonymous to asking a tutor for a text-based hint. And in addition, models of student behavior that drive these systems' automated interventions do not typically consider the effects or even the possibility of teacher interventions, which could severely undermine their accuracy. So to begin investigating teacher behavior, We ran a study in 9 middle school classrooms with a total of 135 students across 4 teachers. And each of the students interacted for 1 hour with Lynette, which is shown here. It's an intelligent tutor for algebraic equation solving, which has previously been used in many other studies in our lab. And from this study, we collected both intelligent tutor log data and classroom observation data using a tool that allows human observers to record timestamps for both the approximate start and end times of any given observation. So we first requested up-to-date seating charts from every teacher before each class session and made sure they adhered to those seating charts, both to enable coding of student-teacher interactions and for use as classroom maps eventually in SPACLE replays. And during each class session, a field observer recorded instances of student hand raising or lowering as well, and coded teacher behavior moment by moment according to one of 6 categories. For each of these categories, if a teacher was interacting with a particular student, the teacher's position was recorded as that student's name in the seating chart. And if the teacher was talking to a particular student, the conversation was labeled as on task if it was identifiably related to the tutor activity the student was currently working on, and was labeled off task otherwise. This was distinguished from cases where the teacher addressed the whole class. For example, to give a mini lecture based around a particular misconception they may have inferred while walking around their classroom. However, we found that these whole class interventions were very rare across the classrooms we observed. Most were one-on-one interventions. We also recorded whether the teacher was monitoring a particular student by standing directly behind that student and observing their work on screen. And finally, we recorded whether the teacher was outside of the classroom entirely, or whether the teacher was inside the classroom but engaged in an activity other than one of the above, such as grading papers or checking their email, or maybe talking to another teacher at the door. We use computer-based pre- and post-tests, which were focused on measuring students' procedural skill in algebraic equation solving. And for the pre- and post-test, we used 2 test forms, which were identical up to the particular numbers used in equations. And we counterbalanced these forms across the pre- and post-test. After using Lynette for 1 hour, students went from an average score of 43% on the pre-test to 52% on the post-test. And this improvement was statistically significant and comparable to results we found from previous studies with Lynette of similar duration. So to gain a sense of how students' learning gains may have been mediated by teacher behavior in the classroom, we analyzed data from 2 class sessions using SPACLE replays. And we often reran these replays with different sets of analytics in order to investigate particular questions more deeply. So I'll highlight just 3 observations that caught our attention. First, teachers tended to monitor their classrooms in short periodic bursts and seemed to selectively monitor certain regions of their classrooms much more than others. On average, teachers also spent nearly half of the class time either inactive or outside of the classroom. Second, although in post-study interviews with some of these teachers, they suggested that they knew which students were most likely to be off task and that they kept a closer eye on these students, the replays seemed to suggest that the most severe cases of off-task behavior were routinely overlooked by teachers. And finally, as I mentioned earlier, it seemed students' likelihood of being off task may have been related to the teacher's proximity in the room at any given time. Similarly, it seemed from watching these replays that students may have been more likely to raise their hands if the teacher already happened to be very close by at that moment. So to investigate the robustness of some of these patterns, we then used synchronized data sets generated from SPACLE to look at relationships between the frequency of certain teacher interactions for individual students and student scores on the post-test. And we were surprised to find that neither a student's frequency of on-task conversations with the teacher nor their frequency of hand raising were significantly correlated with the post-test, even when controlling for their pre-test scores. Interestingly, the failure to detect a relationship between on-task conversations and student learning outcomes is consistent with prior findings by Ryan Baker and others. Although, as those authors have noted, the absence could be due to a selection effect. So students who are doing poorly may be more likely to have these on-task conversations with teachers in the first place. Interestingly, the frequency with which a teacher directly monitored a student was the only measured type of student-teacher interaction that correlated significantly with post-test. And this relationship held even when controlling for students' pre-test scores. So we wanted to better understand the mechanisms by which this apparent link might arise by searching for possible mediating learning behaviors in students' interactions within the software. We adopted a causal model search approach using the PC search algorithm in Tetrad, which is a freely available software for causal modeling developed at our institution, Carnegie Mellon. The PC algorithm is asymptotically reliable under a few assumptions, which are important to keep in mind when interpreting the resulting models. First, this approach assumes that the underlying relationships can be modeled as approximately linear. And second, it assumes that there are no unmeasured common causes, which is almost certainly not true in our case, although we'll relax that assumption in a moment. So shown at the left here is the directed acyclic graph found by PC. Nodes show observable variables from both log data and classroom observations, and links between nodes are tagged with parameters indicating the estimated strength and direction of a relationship. And worth noting is that under this model, the relationship between direct monitoring and students' post-test performance is partially mediated by students' hint use behavior. So if this model is to be believed, it seems more frequent direct monitoring by a teacher may support student learning in part by decreasing their likelihood of abusing hints in the software. However, as I mentioned before, PC made the strong assumption that there are no common causes that we've neglected to measure, which is essentially never true in our domain. So at some cost to sample efficiency, we relax this assumption by using the FCI algorithm, which permits the possibility of hidden causes. And the partial ancestral graph found by FCI adds a bit more nuance to the mediation analysis. So it may be that more frequent direct monitoring by a teacher decreases hint abuse, or it may be that frequency of direct monitoring by a teacher and a student's hint request rate share a common cause that we simply haven't yet measured. So future studies would be needed. Or a combination of these explanations could also be true. However, this equivalence class does preserve the directed link from teachers' frequency of direct monitoring and student learning outcomes, despite some uncertainty about how exactly that link may be mediated. Interestingly, some recent work from Stang and Roll found similar results in a quite different context, introductory physics labs at the university level. So in their studies, they recorded teachers' physical position in a very similar manner and found that the frequency of TA-initiated interactions with students was positively associated with those students' engagement, but consistent with our observation of a possible effect of teachers' mere monitoring of students. These authors found that the length of these interactions did not seem to matter. The authors proposed two possible explanations for their finding. One they called the policing hypothesis, which we might also interpret as a teacher cares hypothesis, a bit less negative, in which frequent teacher visits are motivating to students in and of themselves. And another they called the ventilation hypothesis, in which frequent teacher visits open the door to discussions that are productive for engagement and perhaps learning. Given that both of these explanations seem consistent with our data, we returned to SPACLE replays, this time visualizing students' rate of hint use moment by moment. And examination of these replays revealed that students seemed more willing to use the tutor's hint functions at a high rate when the teacher was not nearby, perhaps providing some weak qualitative support for the policing or teacher cares hypothesis. So this might be viewed as preliminary evidence that students gaming the system behaviors, as documented previously in the intelligent tutoring system literature, may actually extend beyond their interactions within the software itself, maybe suggesting more of a notion of gaming the classroom. However, to know more conclusively at this stage, it would be ideal to run an experiment in which teacher behavior is manipulated, either by having a teacher act as a confederate in a classroom in vivo experiment, or by designing teacher support tools that can nudge teachers towards particular patterns of monitoring behavior. To summarize, we've demonstrated that spatial replay analyses can facilitate investigations into ways the dynamics of a physical learning environment might influence learning within educational software. And our findings so far suggest that The importance of spatially situated out-of-software interactions may have been previously under-considered, at least in the educational data mining and intelligent tutoring systems community that typically examines software log data alone. Some of our next steps include automating the collection of classroom observation data using physical sensors so that we can conduct finer-grained analyses of student and teacher behavior. For example, we're currently exploring the use of inside-out positional tracking to track the location and movement of teachers in physical classrooms. We've also presented some convergent evidence that the mere act of a teacher monitoring a student more frequently may have a positive impact on that student's learning outcomes, perhaps in part by reducing their likelihood of gaming the system or going off task. But to our surprise, we weren't able to detect an effect of the amount of on-the-spot help a teacher provided. So in future studies, we plan to analyze teacher-student interactions at a finer-grained level, distinguishing between different types of assistance that a teacher could provide, and conditioning analyses as well on students' current need for help. In future work, we also plan to conduct quantitative analyses using more local measures of student learning, as well as temporal analyses. And finally, since the pre and post test used in this study was largely geared, as is the case with many intelligent tutoring system studies, to measure students' procedural knowledge, we'd like to investigate whether we might observe more benefits from a human teacher's help on conceptual knowledge. More broadly, in future work, we'd like to better understand the complementary pedagogical strengths of humans and adaptive educational technologies to hopefully inform the design of a more effective blend in blended learning. Thank you.
Open floor for questions.
So those were based in part on the, at the end I mentioned this study previously from Stang and Roll at the university level. That coding scheme was largely identical, but the on-task versus off-task conversation distinction was actually adapted from some of Ryan Baker's work, which also studied it focused more on student behavior in classrooms. No, and we hope to make that more feasible by automating some of the data collection to free up the human coders to then record some of that. Yeah, and we definitely expect that.
What about the teacher's response? Do you think that it changed their behavior a little bit when they saw some of the visualizations? You know, so the next time they use the ITS with the students, they may have, you know, tried to adopt some kind of reflective practices.
That's actually some of our current work. So we're really interested in that. Unfortunately, that time when we showed the teacher, we didn't get to observe them closely after the examination period. But I'm very interested in how this kind of after-action review of teacher position might influence their behavior, because some of the teachers were a little shocked at, they perceived that maybe at most they'd spent 2 minutes in the back of the classroom. It was actually 30 minutes.
Yeah, you all can reflect on teaching practices when, you know, you're, you know, in a situation where, you know, you then can see your own data as well.
Yeah, and they were also shocked by seeing all in those visualizations, the green that seemed to be strongly correlated with them being out of the classroom. Or
Just a funny thing, when we were in classroom one time with this teacher, she was quite brilliant, so what she did, she had every screen in certain colors. She could just stand at the back and she could see if it was someone's on the white screen, she knew they were off task.
wow, I love that. Yeah. Yeah, I was talking to Ito Roll yesterday, and I heard a story from a teacher he'd interacted with years ago in a study, who actually believed that this frequent monitoring of students in these lab sessions, especially at the middle school level, is very important to keep them on task. So she actually put a piece of, I believe, a note card by every computer, and would tick off how many times she's visited each time to just make sure that she's not neglecting certain students. That's good coverage.
I have a question. Do you have any constraints you have to use ITS to be connected to the system, or it can be a applied to anything?
It can be applied to any educational software. So in our case, our group was particularly interested in ITSs, for the time being at least, but there's no constraint to stick to that. Another convenience, I suppose, that led us to choose ITSs here is that we had a number of detectors developed in the EDM and learning analytics communities, ready-made for ITSs. And some of these had been shown to generalize reasonably well across different intelligent tutoring systems. So it was a good opportunity to build on this prior work.
I have a really mechanical question. What was
Sure.
the normalization technique you used for logs from your educational software? What were the log files called?
DataShop. So DataShop and LearnSphere, it's a large educational repository centered at CMU. I believe they're moving to the name LearnSphere, but keeping the name DataShop since a lot of people know it by that name.
Another question. I was thinking about the automation, and you already mentioned if you guys current work on automating the detection of the teacher.
Yeah.
So I was wondering about the orchestration, how to create the map of location for the students. If you have any idea about how to automate that part, because if it now it's supplied by the teacher, that's probably something the teacher needs to do, or maybe you can take advantage of students logging in the computers, or what is the plan in that regard?
So to track student behavior, motion in particular, the question?
Location of the students.
So you can see that this is one other reason why we started with intelligent tutoring systems. We typically, though not always, have stationary students as the default and a mobile teacher, so we had only one thing to track at a time. And without automation methods, that was much easier for human coders. We'd like to start tracking student motion because students do indeed move even though they're supposed to be seated in these class sessions. And there's a lot of actually potentially productive collaboration that happens in these classrooms, even though, again, as others have noted, the systems weren't necessarily designed to facilitate that. So I do know of some studies that have tracked that, but they've all been manual so far. We are interested in moving to collaborative learning settings soon, at which point that will be crucial. Yeah.
That kind of leads to the question of what are your ideas about tracking this kind of student-to-student collaboration? I think many of us have seen it in the classroom situation, and we don't really know how to deal with it because it changes all the models and screws up your analytics.
Yeah.
Moment.
So student-to-student collaboration, even in terms of just analyzing log data.
Yeah, but also what happens when one student comes over to another student and, either, contributes to an idea or solves a problem for the student or takes an idea back, to their group or to their, them as an individual. I think that's something that's very kind of, hasn't really been looked at yet. It's
Yeah.
kind of in the classroom situation, what happens. In the lab, of course, you can't do that because, it's one group of students or two groups of students and there's no kind of interchange. But in the real classroom, of course, there's a lot of cross-pollination. Whether that's positive or negative is, in terms of the students, is something really interesting to investigate.
So I actually, I'll make a plug for a professor at Carnegie Mellon, Amy Ogan, who's working with a student, David Gerritsen. Amy historically has really pushed on this idea that despite not necessarily being designed for collaboration, ITSs are used for collaboration in classrooms. Recently, she's been shifting into kind of equipping classrooms with sensors, the cheapest sensors they can find that can record this type of behavior at a fine-grained level. From what I can tell, that actually often involves placing sensors at every single student's desk. But they're starting there and then trying to look for cheaper ways.